Hey guys, it's John the Quant here. Before we get started, I do have COVID right now. I feel fine except for this cough that will not go away. So if you see me coughing a lot throughout this video, well, that's why. And then about the channel, I know I haven't released anything in a while, not since that super fast course on interest rate swaps. And what happened is I really loved making that course. I loved researching it and presenting a lot of information, from a wide variety of perspectives. And I want to keep putting out content that's that high quality. So what I've been working on is another course that's everything to know about linear regression. And that's a big topic. The course has gotten very, very big. It's probably going to have to be released in sections, but it's all done except for the video, so keep an eye out for that in the next couple of weeks or maybe a month. So today, we're going to talk about the machine learning process, and this isn't about any specific part of the process or any specific model or anything. It's about how all the pieces, everything that you would do in a machine learning project, how that all fits together. And to illustrate this process, we're going to look at a simple example. We're going to talk about, what I did, why I did it, and what I was thinking while I was doing it. So it's going to illustrate a lot about the Sci-Kit Learn library, which is a big deal in machine learning. It's huge. And there's going to be a lot of things that we don't get very deep into, but don't worry about that. Remember, this is about the process as a whole and how all the pieces of the process fit together. And because of that, I decided just to use KNearest Neighbors, which is a very simple, very easy, intuitive, easy to understand machine learning model. Actually, I'd say it's not really much of a model at all. It's more like an idea. And there's very little machine learning actually involved with it. But let's go over to the iPad, and I'll just show you guys how it works real quick. All right, we are over on the iPad, and what we're talking about is how KNearest Neighbors works. KNearest Neighbors, or you'll often see it written KNN, just KNN like that. Now, like I said, this is very simple. So let's say that we have a whole bunch of observations, and our observations look like this. We've got an X, we've got a Y, and we've got a Z. All right? Each one of these has an X, a Y, and a Z. And what we're trying to do is we're trying to use X and Y to predict Z. So what we can do is draw a graph, right? This is X here, obviously, and this is Y. And all of these points go somewhere on this graph because they have an X and a Y. Say they look like that. And now, say we've got a test point, and we know the X, we'll call it XT and YT, all right? We know the X and the Y, but we don't know the Z for this one. And let's plop it down. Let's say it comes out right here. Now, if K equals 3, all right, if K is equal to 3, then that means we're going to find the 3 points, the 3 black points, the training points, that are the closest to it, which appear to be these 3. And we're going to say that ZT, the one we're trying to predict, is approximately equal to the average, all right, of those 3. So that's going to be Z1 plus Z2 plus Z3, all right, over 3. That's a very simple way of looking at how that works. Now, that would be for regression. Let's talk about if we had one for classification. Now, it works kind of the same way. So we're going to say that we have X's and Y's for a bunch of these. Let's draw another graph here. This is X and this is Y. And let's say that dots are either blue or they're green. All right, so we've got all these blue dots. All of our training instances, we know that these are blue. And we've got some green ones. And there's probably going to be some overlap, but hopefully they will be separable enough that this won't be too much of an issue. And now we've got a new dot. And let's say it shows up right here. Now again, let's say this time that k is equal to 5. So which 5 points appear to be closest to that black dot? I'm going to say it looks to me like it's these 5 here. All right? So we've got 3 red ones and 2 blue ones in those 5. So what color is the black dot more likely to be? Well, they vote and they say that it's more likely to be green. So we're predicting that that black dot right there is a green one. That new observation falls into the green group. That's how KNN classification works. The last thing we really need to talk about here is how do we decide which 5 points or 3 points or however many points are closest to the new observation. All right? So we're going to need a distance measure. And there are a lot of these. You should definitely look it up. We're going to talk about 2 important ones, very common. The first one is Euclidean distance. And you're probably familiar with that, all right? So the Euclidean distance between 2 points is going to be the square root. We're going to take all the different values, x1 minus xt, and square them, plus y1 minus yt, and square it, and so on. So in general, this would be the square root, all right, of the sum from I equals 1 to, I don't know, n of x of I minus, we'll call it xt squared. So however many features you've got, if that's 5 features, what you're going to do is you're going to take the feature from a training point, subtract the feature from the new observation, and square it. Add all of those up, and then do the square root, and that's going to give you the Euclidean distance over there. The other common one is called Manhattan distance, and it's very similar. The difference is instead of the square root, you're using absolute value. Instead of the square root and squared, you're using absolute value of each one of these. All right, so that's the sum from I equals 1 to n of the absolute value of x of I minus, we'll call it xt. All right, so for each of your features, you're going to take the feature from the training point, subtract the value of that feature from the new observation, get the absolute value, and add all those up, and that's going to give you the Manhattan distance. Those are the 2 main ones. We're just going to use Euclidean distance, I think. But that's how KNN works. Very simple, very intuitive. The machine doesn't actually have to learn anything. It just needs to remember where all the training points are, and then it can calculate the distance, find the nearest ones, and either have them vote or take the average. All right, let's head back into in-person and talk about what happens next. Now that we know how the model works, and it is very intuitive, isn't it? Let's talk about the steps we're going to go through the process, and hopefully I can make a nice graphic that pops up and shows all this. But all right, so there are a few steps, and a lot of these, there's so much overlap that I had a hard time kind of deciding what the order is, and it's why there's so much disagreement if you look up machine learning process. Is because there's so much overlap between steps that it's really hard to put them in order. But this is what I've come up with. This is my machine learning process. So number 1, I think it is incredibly important to understand the problem that you are trying to solve. All right, you've got to understand the problem, or how are you going to know what features might be interesting, or what model you might want to use, or anything like that. And we'll talk about that a bit more when we look at the example. Step two, you've got to get the data. You can't do any kind of machine learning without data. You've got to get it from somewhere. There's a lot of data available online. We're going to be using a Kaggle data set in this example. Number three, you might see these listed separately, but I put them all in the same step because they're things that I think you need to be doing together. All right, and that's explore, transform, clean, and engineer features. I think you need to be doing all of those at the same time. All right, while you are exploring any sort of errors in the data or anything that you come across, you need to clean those. And if you come across some feature that needs transformation, then go ahead and transform it. Or if you think of an interesting way to handle the features, go ahead and engineer your new features right then. I put that all into one step, all right? Explore, transform, clean, and engineer features, all in step three. Number four, I put this separately as encode your features. This could be one-hot encoding for binary features or ordinal encoding, whatever it might be. I think you should encode them after you've explored everything, and we'll look at how I do that. The next step is feature selection. So chances are, once you've come out of those two steps, you're going to have a lot of features, especially if you do something like one-hot encoding. You could end up with thousands of features, and you may not want to include all of those in your final model. Maybe you do, but there are a lot of ways to select which features to keep, and you might end up just keeping all of your features, and that's fine. Number six, once you've selected them, is doing the actual modeling. And there's not a whole lot to this step. Once you've got your features and you have an idea of what's happening inside the features, then you should be able to pick a good model to run to get your answer. And then number seven is evaluation. All right, just evaluating the model. We're going to look at a lot of different metrics. We're going to look at plots and things like that. And then number eight is just to repeat the steps as needed. So say you've gone and you made this model, and it's not giving you the performance that you need it to give you. So you might think, oh, well, I need more data. In which case you'd have to go all the way back to step two, getting the data, and then you'd have to go back through exploring, cleaning, transforming, and engineering features. You'd have to encode features. You'd have to select features. You'd have to create a new model and then evaluate it again. Or say you got to the end and you're like, you know what? Making that one feature binary rather than letting it be numeric was a bad idea. So you might just go back to the encoding features or exploring features section and then walk back forward. But wherever you go back, you've got to go through the rest of the process all over again. So that's easy enough. There's 8 steps, and one of those steps is to repeat the previous steps. So let's just go over to the computer and look at this example. All right, so here we are. This is a machine learning process workthrough example. So here it says we're going to use an application of the KNearest Neighbors algorithm because it is super simple to show the machine learning process. And that's true. I'm going to zoom in a little bit if I can here. Wrong button. There we go. All right. So the problem that we're going to end up solving is actually going to be predicting home prices. And it's very easy. It's a very common thing to do. So first we've got some imports. We're going to filter warnings and just ignore them. We'll be using pandas. We'll be using NumPy. We've got matplotlib and seaborn here. Pathlib and zip file are going to be used to help us downloading the data set. We'll be using SciPy for the Spearman rank correlation function. And then from Sci-Kit Learn, we're using a KNeibors regressor, KNeibors classifier, and then we've got a bunch of different scoring functions. We'll use a pipeline later. And from Yellow Brick, which is a very, very cool kind of graphical library, we're going to use validation curve and learning curve. And we'll look at how all those things work later. So step one is to understand the problem, right? And because this problem, it was just kind of chosen because the data was available. There's not a whole lot to it. We're predicting home prices. We're just predicting home prices. It's kind of a toy example. Let's keep going. Not a whole lot to understand. So, getting the data. We're going to use the Kings County housing data from Kaggle. You can get it directly from the API. This is the function or the call that you would use, the API call. Kaggle, datasets download, -d, and then the person who uploaded it and the dataset name. So it downloads as a zipped folder. So we're using zip file, all right, to extract the information from there. Then the path to the CVS that we extracted just follows this. It's in the house sales prediction underscore data folder, and it's called kc underscore house underscore data.csv. So now that we've got that path, pd.read CSV just to bring it in, and just drop some stuff that doesn't matter, latitude and longitude. I don't care about that, date, whatever. And look at what we've got left. So this price column is going to be our target. We're trying to predict the house prices. And we've got information on the bedrooms, they've got the bathrooms, the square feet for the living space, the square foot of the lot, how many floors it is, whether or not it's waterfront, if it's got a good view, what condition it's in, what grade it was given. These are pretty similar, I think. Square feet above ground, square feet in the basement, the year it was built, whether or not it was renovated, and then a couple of others that I'm not 100% certain what they mean, but it's not all that important. We can see this one. The non-null count is exactly the same for every single one, which means we're not going to have missing values. All right, it's exactly the same as this range index as well. So there are no missing values in our data set. We can see that right here pretty easily. And then it tells us the data type that each one is, whether it's a floating point number or an integer are the only two. So now we're on to exploring, transforming, and engineering features. Now we sort of explored a little bit already by looking at whether or not we had missing values and what kind of data type we're working with. But then I am a big fan of box plots. Some people think they're kind of outdated, but I started using them in grad school, and there's a lot you can learn with a box plot. So that's what I started with. And Seaborn just makes a box plot real fast. And what we can see here, if we look especially at this price one, most of them are squished. But price, which is our target variable, we can see that it's pretty crazy. It looks like it's somewhat symmetric down here, but then look at all of these outliers. So we can see that it's got just these crazy, crazy skew. So if we go further down, we'll use a dist plot to look at that skew, and we can see that it's kind of bunched up here, and then it goes down. Now, KNearest Neighbors is what we call a non-parametric model, meaning that it doesn't really care if your data is symmetrical or not, or if it's normally distributed or not. But so many different models do care about that stuff that's probably better off just to transform everything to try to make it normally distributed anyway. So looking at this, what I'm kind of thinking is that an exponential distribution starts really tall and then goes down really fast. So if I'm thinking this kind of looks like a mockery, I guess, of an exponential distribution, then the way to fix that would be to do the opposite of exponential, which is to do a log transformation. So if we take that price column, which is our y, and just do a log transformation on it, doing the natural log, and then look at it, now it looks centered. It looks pretty well normal. And that's what we want. So then further down, I did another box plot, and we can see these two especially, square foot lot and square foot lot 15, seem to be very skewed as well. But what I decided to do, since so many things were just squished, that I thought I'd just do a box plot for each feature separately. So we can see bedrooms is pretty squished, and it's got outliers on either side, especially this one way up here. Bathrooms, again, has high outliers as well. Square feet living, square foot lot. Floors is going to be a weird one. We can tell just by looking at it. Waterfront is already binary, zeros and ones. View has a rating between 1 and 4 and appears to be only integers. condition, we can see that the median line is not in the middle, so it is skewed. We'll have to look at what that feature means. It also appears to be integer only. Grade is also integers, but it looks like it might be spread out enough that we could treat it as numeric if we wanted to. Square feet above has the high outliers. Again, square feet in the basement seems to have a lot of zeros and then some other stuff. So we're going to have to really look at that one. Year built looks somewhat normal actually right now, but we'll have to get a closer look at that. Year renovated appears to be more or less binary. It's either 0 or it's something close to 2000. Square feet living is also skewed, and square foot lot 15, whatever that means, is very highly skewed, and we're going to have to work on that. So further down, I'm going to make a list of features that are numeric or features that are categorical. And I'm going to stop right now for a second because I've got to get some water, and I'll be right back. I'm back. Now, what we were just talking about was we're going to make a list of features that are numeric or categorical. And we're pretty lucky here in that we've only got, what is this, 3, 6, 9, 12, 15. It looks like about 15 features. So that's not that many. All right. If we had hundreds of features, we wouldn't be able to do what we're about to do. But because we've only got 15, we're going to go through every single one of them separately and have a look around in them and deal with them each individually. So let's look at bedrooms. All right. We'll start up with a value count because bedrooms is going to be a whole number. And you can see this weirdo down here. It says there's a house with 33 bedrooms. Does that sound reasonable? Not to me, it doesn't. So let's just look at that observation, the house with 33 bedrooms. So there's 33 bedrooms, there's 1.75 bathrooms, and 1,600 square feet. And that's not real. That can't be a real house. That's absolutely no way. So we're going to say that that was meant to be 3 bedrooms instead of 33. So we're just going to change that down here. 3 bedrooms instead of 33. But there was also one that had 11 bedrooms. So we'll look at that. It says there's 11 bedrooms, 3 bathrooms, 3,000 square feet. Now, it was built in 1918. So just knowing a little bit about older houses, there were typically very few bathrooms and sometimes a huge number of bedrooms. So this could be real. This could be a very old house with 3 bathrooms, a whole bunch of little bedrooms, all kind of squished together because it's not a very big house. So this could be real, and we're not going to mess with it. But because they're all integers, we're going to say that this is a categorical variable. And that's a choice that you get to make. Is this categorical or should we treat it as numeric? We're going to treat it as categorical. So I'm appending it to that categorical list. Next, bathrooms. We'll look at the value counts there. We had 10 houses with no bathrooms, which is weird. A lot of them with just a half, and then some of them, going all the way up to 8. Now, this honestly looks like there's enough of it to treat it as a numeric value. So let's look at a distribution plot, and we can see it's pretty wonky. But we're going to treat it as numeric, and I didn't do any kind of transformation here. We're just treating it as numeric. Now, if we look at the living space, we can see that it is also skewed. So the same general idea as with price. If we do a log transformation, we would expect it to be more centered. And we do the log transformation, and it is, and it looks good. So we're going to call that numeric and go ahead and append it. Square foot lot, look at this thing. This is very, very skewed. So we are absolutely going to try a log transformation on that, and it still looks a little weird. So what I'm doing here is I've taken the from the stats models API, using a QQ plot to see how close does this weird bumpy distribution actually get to a normal distribution. So if it was a perfect normal distribution, all the dots would be on this line. Now, as you can see, they're not all on the line, but they're mostly pretty close except for this bit up here. So I'm going to say that that is close enough. All right, this is part of the art of statistics or machine learning or modeling in general. Is this close enough to normal to meet that assumption? And I'm just going to say yes. Again, KNN is non-parametric, so it doesn't matter so much. Right? The QQ plot shows that this feature is normal enough, is what I wrote here. So I'm going to append that as another numeric feature. Now then, floors. I was a bit taken aback by this. I thought it would be all integers, but apparently you can have 1.5 or 2.5 or 3.5 floors. Whatever. What is a half floor? I do not know. All right, but we're just going to leave it. We'll end up treating it as categorical. So I put that as categorical there. Now, waterfront was zeros or ones. It's all binary, so we treat it as categorical. It's super imbalanced. See, almost all of them. 21,000 of them were not waterfront and 160 were. So there's not going to be, probably not going to be a lot of information involved in that feature, but we're going to keep it for now. We'll deal with that in the selection process. Now, view got rated from 0 to 4. I assume 4 is the best. I don't know. In any case, it's also pretty imbalanced, but we'll keep it. We'll just call it categorical. They're all integers. Keeping going. Condition was rated from 1 to 5. Again, it's categorical. We're just going to keep it categorical. Grade. Grade went from 1 to 13. And if you look at these, it kind of looks like if we were to plot them, they would be pretty normal shaped. But because it was integers, I decided to treat it as categorical. You probably could have treated this grade one as numeric if you wanted to, because there's enough values and enough difference in the values. But I decided to treat it as categorical. Square feet above, looking at that, a little skewed. Trusty log transformation there, made it much more centered. Append it to the numeric list. Now this one's interesting. This is square feet in the basement. You can see that there's a whole lot of them that are 0, and then a bit of a slope. So what I decided to do, I thought maybe the size of the basement is important, so I didn't want to get rid of it. But the fact that there's a lot of zeros and then just a few that aren't zeros, I decided to make it into a binary variable. Has basement. I created a new feature here. Has basement that just says, is the square feet in the basement greater than 0 or not? So you can see 13,000 of them have no basement, and about 8,500 of them have a basement. That's not too bad. So we're going to keep them both. Keep the new binary one as categorical. Keep the original as numeric, and see how much information we can get in each. This one is also complicated. This is the year that it was built. Now, looking at the distribution, it looks almost normally distributed, especially through this section, but it's got this weird section. A log transformation certainly wouldn't make this normal. We could have binned it, maybe, turn it into a categorical variable using bins. Could have made it binary, maybe cutting it through here like 1935 or something and keeping old houses in one and these houses in the other, maybe 1940. But what I decided to do was called a Box-Muller transformation. And let's actually go through that Box-Muller transformation, and I'll explain how it works, and we'll come right back. All right, very quick overview of the Box-Muller transformation. So what this does is it turns a uniform random variable into a normally distributed random variable. And it actually takes 2 uniformly distributed random variables to make the transformation. And it can return 2 normally distributed random variables. And this is the function. All right, so you have uniform random variables U1 and U2. and we're going to get normally distributed random variables z1 and z2. So to get z1, you'll take the square root of -2 times the natural log of u1 times the cosine of 2 pi times u2. That's going to give us z1. And then to get z2, you're just exchanging, instead of u1, you're using u2. Instead of u2, you're using u1. And instead of cosine, you use sine. And now we're just going to show you that that works. So I've just imported what I'm going to use here. u1 is going to be a sample, all right, from a random uniform random variable size of 10,000. u2 is the same. We'll look at those two distributions, and they definitely appear to be uniform, which is good because they are. So here we went through the actual transformation, all right, the square root of -2 times the log of u2 times cosine of 2 pi u1, and then switch 1s and 2s basically here. Then I plotted the new ones, the new random variables, z1 and z2, and they look very normal, right? And just to show that they are normal, I did a couple of QQ plots, and you can see that they fall pretty much entirely on the line, which makes them Gaussian or normally distributed random variables. All right, let's go back over to the walkthrough presentation. Over on the walkthrough, we were looking at this year built variable, and I was looking at it and thinking, this almost looks kind of normally distributed. And I thought about binning it, like I said, but I decided kind of uniformly distributed. So what I wanted to do was that Box-Muller transformation. But I only have one random variable. So what I did was I made another uniformly distributed random variable by just taking that year built random variable and dividing it by the maximum. So that just gave me a new uniform random variable that was between 0 and 1. And they actually ended up being like between 0.9 and 1, but it doesn't really matter. So then I called this test because I was just testing it out. I used that U1 and I used the original year built column as U2 and did this Box-Muller, transformation, and look at this new distribution. Now it's definitely still not normally distributed, but it looks much closer. And if we look at this QQ plot, it does a lot better in the middle. Now, again, this is one of the times when as a machine learning, scientist, you just kind of get to decide if you think that is normal enough. And for right now, I think that's normal enough. It looks actually surprisingly good compared to how it started on that QQ plot. So I've decided to leave that and append the year built column to the numeric features list. Now for year renovated, we can see it's basically either 0 or it's something around 2000. So we're just going to make that binary. All right. It was either renovated, meaning it has something greater than 0, or it wasn't, which means it's 0. And you can see there's about 21 times as many that weren't renovated as were renovated, but that's okay. We're going to append that to the categorical features list. Square foot living 15, we can see it is, again, skewed. We're just going to do a log transformation there, like we've been doing a bunch of times so far, to get it pretty bell-shaped, pretty centered, and append it to the numeric column. Now this one, square feet lot 15, that's very skewed. So when I did the log transformation, that made this weird bumpy thing. This shouldn't be there. Let's fix this. There we go. All right, but still, it made this weird bumpy thing, right? However, on a QQ plot, it looks all right. It's pretty close. If you had like a fat pencil, call it the fat pencil test sometimes, a QQ plot. If you had a fat pencil and you laid it down over this, it would cover pretty much the entirety of the blue dots. So that generally means it's close enough to normal, not to worry about. So we're going to append that to the numeric features list. Now, the next step. All right, so what we've been through so far, we got the data, and then we explored it, we cleaned it, we transformed it, and we engineered some features. Now, exploring was looking at all of those box plots and distribution plots, and cleaning was looking at whether or not the values seemed real. Um, Especially the ones where we had the bedroom, it had 33 bedrooms or 11 bedrooms. We definitely cleaned that up. Now, transforming, we did a whole bunch of that, mostly log transformations, but also we did that Box-Muller transformation. And then engineering the features was really when we took the ones that were not binary and made them binary. That definitely counts as feature engineering, but there's a lot more that you could do, and we'll cover we'll do more extensive coverage of feature engineering techniques at a later date. But mostly what we needed to do in this one was binarize things or do transformations to make them kind of normally distributed. Then I brought in a one-hot encoder. And we're not going to talk about what one-hot encoding is, but really if you have something that's categories, basically if I have 3 categories, I'm going to turn that into 3 different columns that all only have zeros and ones. Now, remember, we were appending the feature names to either a features numeric list or a features categorical list, and this is why. We're going to look at all of the numeric features and check their data types. And you can see they're mostly floats, but we decided to treat these two, the square feet in the basement and the year built, which are integers, as numeric data. So we want to change those into floating point numbers. So I just went through all of the features in the all of the numeric features in our xall data frame and changed them to floating. And then you can see they all came out floating. Now, if we look at the categorical features, we have most of them are already integers, but floors is floating. And if you remember, that's because floors had these 1.5, 2.5, 3.5 story buildings. And if you change this into an integer, it's just going to cut off the decimal. So instead of saying 1.5, it's just going to say 1. And we don't want that. We're going to be losing information if we do that. So the workaround that I came up with is just multiplying these all by 10. Now instead of 1, 2, 1.5, etc., we have 10, 20, 15, and so on. And now when we change that into an integer, all right, we'll cycle through all of the categorical features and change them to integers. Now instead of 1, 2, 1.5, we have 10, 20, 15. And we've kept those different groups. And again, because it's categorical, especially if you want hot encoding, then the scale of the groups doesn't matter. So this is a great way of handling that. So now let's look at the data types for all of our features and just kind of make sure that the ones that are integers look like they're supposed to be integers and the ones that are floating seem to be numeric. Now down here, I ended up not using the one-hot encoder. And the importance in that is because of the model, all right? The model choice. And what I'm going to do for feature selection later. The KNN model doesn't really need one-hot encoding. If I was doing linear regression, I would absolutely use a one-hot encoder, but in this case, we don't need it, and it makes feature selection a little more difficult. So I ended up not using it. Now, for feature selection, I used mutual information regression, and we're not going to get into what that means, but mutual information regression is just a way of determining which features in our feature data frame give us the most information about the target variable. So it's super easy to run. This is just a Sci-Kit Learn function. All right, Sci-Kit Learn feature selection mutual info regression, and you just put in your x and your y, give it an, and then I turn that into a series because I wanted it to look like this when it came out. So what it did was it ran that algorithm, and this tells us the higher the number, the more information about y we are getting from x. So this tells us that like the grade of the house gives us the most information about the price of the house. The next is the square feet of the house. Bigger houses are more expensive. The next one, square foot living 15. I imagine that this is highly correlated with square feet living. Now we did not look at correlation at all, correlation between features really at all, because again, KNearest Neighbors doesn't really mind. But if we were doing linear regression, that would matter a lot, and we would absolutely have looked at that toward the end of the feature engineering and feature exploration section. And you can see that year renovated gave us very little information, and that's probably due to the fact that it was very imbalanced. Waterfront also. Things that are very imbalanced tend to not give a whole lot of information. Now we're going to keep just the 10 highest, the 10 most important factors from that mutual information regression. And I've made these scatter plots. These are SNS.pair plots, and they're just between the 10 factors that we kept, the 10 features that we kept, and the target variable. And we can look through these and see how they seem to have pretty good relationships. Grade has a great relationship with price. Square feet living, good relationship. Look at this. It's all, this one's a little less obvious, but it does appear to have a good relationship with price. Some nice correlation between our features that we selected and the target. And that's excellent. That's really what you want. So now we're just looking at the features that we kept. What are they? The grade, square foot living, square feet above, bathrooms. Just to make sure that, once again, we can see that we kept only 3 categorical features, and we kept the other 7 were all numeric. And we're looking at the Spearman correlation, and we're using Spearman because it's non-parametric. If we want to use Pearson, then you've got to deal with a bunch of different assumptions there. But Spearman is more robust to that. So we'll look at how highly do these different features correlate with what we're trying to predict, which we saw back in these plots, that the correlations look pretty good. So down here you can see that grade has a correlation of like 0.65. Square feet living is pretty close behind. And you can see that these correlations are pretty strong, which means we ought to do pretty well with predicting house prices based on those features. So now we're going to get into the actual regression. Now, the one thing we didn't really talk about with KNN, and hopefully I can make the Euclidean distance pop up again. But if you think about the Euclidean distance equation, all right, the square root of all the differences squared. Well, if you have some features that are like 10,000, and the difference between them is 500, then 500 squared gives us, what does that give us? I don't know, 25,000 or something. And then you have other ones where all the values are like around 10. Then a difference in that large feature is going to have way bigger impact than the difference in that small feature. And you don't want that, so you need to scale. You need to scale your features for KNN. They need to all be the same scale. So what we're doing right here, this is a standard scalar from sklearn.preprocessing import standard scalar, and that does the like a z-score. It subtracts the mean and divides by the standard deviation, and so it kind of scales everything to between -4 and +4, somewhere in there. And it also would make it even more normally distributed, but we already made it pretty normal, so that's all right. Now we'll create the model and then fit it to the scaled features and then y. And then we can just predict and look at what our predictions kind of look like. And now we can look at error metrics. Sklearn.metrics has a ton of error metrics available, and some people tend to focus on like just RMSE or something. or mean absolute error. But that doesn't make any sense. Why not just look at everything? Every single metric is going to give you a slightly different kind of information, so you may as well look at everything. So I imported a few different regression error metrics, and we're not really going to talk about what each one of them means, maybe just a little bit. But none of them are that hard to understand. So then we'll get the actual errors, which is the original y minus the predicted y, and then save all the scores. We've got the root mean squared error. All right, so that's the square root of the mean squared error. Makes sense. Then the root mean squared log error. So we're going to get the mean squared log error using this function up here, and then take the square root. Then we've got the mean absolute error, the median absolute error, and the R2 score, which is also sometimes called the variance explained. That's from more classical statistics, kind of way of looking at things. Now, we're just plotting it, okay? We're just making these plots in that section. So this is the predicted price versus the actual log price. And what you want is a clear, hopefully 45-degree, all right, relationship between the two. But definitely you want to see a linear relationship between the two, which we do. So that's great. It means we're doing pretty well. And if we look here, the distribution of the residuals, you hope that that's pretty symmetric. Otherwise, you've got some kind of serious problem in your model where your model is consistently predicting too low or too high. And here we can see that they are normally distributed. So that's great. And then error metrics. You kind of need to understand what the error metrics mean, because R2 score, we want that to be high. It's close to 0.8. And that's pretty good. Absolute error, we want that to be low, and it's pretty low. Mean absolute error, also low. The fact that the median and the mean are not the same does imply that this is a little bit skewed, this distribution, but no problem there. Root mean squared log error is very low, and the root mean squared error is also pretty low. Now, we're going to do cross-validation, and I did this first by hand so we can see what's happening, and then we are also going to do it in a more automated way. So first, I defined my own root mean squared error function, and then used the make scorer function, also from Sklearn, to be able to use that inside the manual cross-validation. So I've got cross-validation, RMSE, then we're gonna, our one real hyperparameter here is gonna be the number of neighbors to keep. So we're gonna keep 1 or 5, or this tells us to do like 5, 10, 15, 20, all the way up to 50. And then for in this list that we've created right here, we're going to put everything into a pipeline, and this pipeline is going to send the x values through the standard scaler, and then it is going to send them through the KNN model, the K-Neighbors regressor, with this number of, with a varying number of neighbors. And then we're going to catch the RMSE, all right, the cross-val score from each of those. So cross-val score is going to take in this pipeline, and it's going to take in our features x, and it's going to take in our target y, and it's going to take in our scoring function, which we made ourselves up here. And then it says we're going to do 5-fold cross-validation, calculate the score, and then save it. And then we kind of just change that into a data frame. Then we'll keep the best in, all right, the best RMSE, and print that. So the best value of k, the best number of neighbors to keep, was 25. And the best RMSE that we got was about 0.3. Now we just want to plot how changing the number of neighbors affected the RMSE. So when we had a very low number of neighbors, we were not doing so great, but then very quickly it went down. But then when you got too many, it started slightly kind of sloping back up. But 25 is about here, and yeah, that looks like about the minimum. Now we do the we're getting cross-validation predictions here, and then looking again at a scatter plot with the predictions on the y-axis and the actual price there. And what we want to see is a clear, uh, linear relationship there, which we do. We can see that they're huddled around this linear line that I made. So that all looks real nice. Now we're just going to look at the error metrics from the cross-validation, all right? So since we got these predictions up here from cross-val predict, that means that it's keeping predictions from all of those cross-validations. So what we can do is save all of them and just very quickly make the RMSE, the RMSLE, and etc. based on those using that cross-val prediction output. And then we're making those same plots as before. Here you can see we've got a very nice linear relationship between the prediction and the actual value. These look pretty centered, pretty good. And then up here, the R2 score is slightly lower than it was before. And these may be slightly higher, but this all looks very nice. That's why cross-validation is important, is because it gives you a better idea of how everything will form on data that it hasn't seen before. So this is how is it doing on data that it hasn't seen before, and it's doing pretty well. Now, we did that for loop, all right, up here. To go back, we went through this for loop and calculated all of this stuff and did it sort of manually, but Scikit-Learn has a very easy way to do that automatically. It's called Grid Search CV. And that is going to take in your parameters, which are only hyperparameter was the number of neighbors. And it's going to go through, we told it to go through 5 folds, all right there. And it's going to use that same scoring function that we use. And it's going to cycle through, all right, all of those different numbers of neighbors, 5, 10, 15, all the way up to 100 now. And it's going to run the thing and get the score for every single one of those. And then it's going to save what is the best model and the best score and everything like that. So here we're just saving things that came out of it. If we look at this plot, this tells us, if you can see these little dots in the middle, that's the mean RMSE for that number of neighbors. And then it shows us how much spread there was. Like for 5 neighbors, it was about 0.307, something like that. But it went all the way up from about 0.315 to about 0.303. And the RMSE went somewhere in between there. But if you look at these, we can see that 25 has probably the lowest mean and definitely the lowest minimum. So it does look like 25 is the best number of neighbors to use. So we've got training and validation curves from Yellow Bricks. This is very cool stuff. This shows us the score that we got for various numbers of neighbors here as well. The training score is in blue, and as you can see, the RMSE actually went up as we used more neighbors for the training set, but it kind of went down a bit and then started to go up for the cross-validation sets. 25 is probably about this one right here. And then further down, this is the learning curve. So this tells us how many training instances, all right, if we use more training instances, does our model learn better? And as you can see, the error definitely goes down as you use more training instances. But you kind of get diminishing returns, especially once you get to about here. And that's everything that we did for regression. Now, I also wanted to cover classification, and hopefully this will go faster. All that we did was we took the target variable and made it binary by saying, is this in the top 50% or not? And again, this time we're scoring using the area under the curve for the receiver operating characteristic. And that sounds complicated, but it's not that hard to use. We're not going to talk about what it means so much, but we will see how it is used later on. But that's going to be our score that we're using. And again, we're using a grid search CV here. Cycle through the number of neighbors. All right, we're going to go 5, 10, all the way up to 151 this time. And we're going to try to fit a classifier, the KNearest classifier, onto X and the binary target variable that we just made. And then we'll save the best number of neighbors and plot a nice validation curve here. So as you can see, this time we want to maximize the score because this time the score is the area under the curve. We want it to be higher. And it looks like 25 is probably our best K again. All right, because it's got a nice little peak on the cross-validation score, and it's not yet to the point where the training score has become a problem. Now we go down, look at the learning curve here. All right, how many training instances do we get? We can see that it goes way up at first, and then we kind of get diminishing returns, especially when you get to about here. So even when we were doing regression versus the binary classification, these models are actually performing very similarly. And then there's a lot. There's just a freaking ton of classification error metrics. And they all, again, tell you slightly different things. We're not going to talk about what each of these means, but they're all available in sklearn.metrics. So you should definitely look more into them. And we'll get the cross-validation predictions here, which is going to predict a probability. And it's important to predict a probability for a lot of those metrics. And then we'll get we'll make a pred scores dictionary that has the true values and the predicted values, which is called y-score. And what's cool about doing it like this is that in these functions, like you can get the area under the curve score. You can do this double asterisk notation, which is very cool. It's very quick, very easy. And we can see our ROC AUC score, which has a maximum of 1, is 0.85, which is great. It's really very good. For how little we've actually done to get that score, we're doing great. And then we're just kind of making some things so that we can make some plots later. And this F1 score, that's telling us the best threshold. This is if your probability of being a 1 is higher than 0.38, just call it a 1. And we're just going to make these plots. So look down here. This is the ROC curve. And what this does is it changes that threshold, okay? The point at which we say if the probability is above this number, then just call it a 1 and else call it a 0. It changes that, and it has the false positive rate or the specificity on the bottom and the true positive rate or the sensitivity or recall, right, on the y-axis. And this curve, the area under this curve, it tells us about the accuracy, I guess, of the model. If it was directly on this line, then that means you're about 50-50, no better than just randomly guessing. But if it was all the way up here at 1, that would mean it got everything right literally all the time. So this curve and having an area under it of 0.85 is very good. All right, precision recall curve. Again, we're changing the threshold and seeing what happens to the difference. All right, if we can raise precision, but we've got to, if we want to raise precision, then our recall is going to go down. And this just kind of lets us see what that looks like, what kind of relationship those two have. And then the F1 score, as we change the threshold, what happens to the F1 score? And F1 is it's the harmonic mean between precision and recall. So it's kind of a balance between the two. So we want to maximize the F1 score to get a good balance between precision and recall. And this dotted line is that 0.38 threshold where we set our maximum F1 was. So all of these plots actually look fantastic. I'm surprised at how well this model has done with how little work we actually did to make it. to make it work that well. You can see our average precision score was actually 0.85. Again, phenomenal. I accidentally printed that. Oh, didn't mean to do that. All right, so we've got Breyer score loss. In general, like I said, there's a whole bunch of different metric functions. In general, if it is a score, you want it to be higher, and if it is a loss, you want it to be lower. Just in general, it doesn't always work that way, but because I don't want to explain every single one of these, that's kind of the heuristic we're going to look at. So since it's a loss, we want it to be small, and 0.15 seems pretty small to me, so that's great. And then we're going to set the threshold, okay? So if the y-score, which was a probability, is greater than that best threshold of 0.38, we're going to call it a 1. Otherwise, we're going to call it a 0. So now this is a column of 1s and 0s. And we're going to call that scores. And it's going to let us use this double asterisk notation, which is very cool. And again, if it's a score, we want it to be higher. 0.78 out of 1, that's pretty good. Classification report here tells us the precision and recall and F1 score, and importantly, it also gives us the support. So this tells us that 0s and 1s were very well balanced, and that's because we binarized that target ourselves, and we just said the top half make them 1s and the bottom half make them 0s. If you had very imbalanced classes in the target, then that would make these here less indicative of actual performance. All right, so we can see these are all pretty good numbers. The lowest one being the recall on 0 is 0.68, meaning that it's missing some of those true positives, or some of those true 0s it's predicting are 1s. We can see the accuracy score, 0.76, that's pretty good. 0.1 loss, we want it to be lower. 0.23 is pretty low. Hamming loss, 0.23 again. Actually, these appear to be exactly the same in this case. Cohen's kappa score, this one's complicated. 0.5 is okay. It's not great, it's not awful. Hinge loss, 0.73. Jacquard score, 0.64. Log loss, I'm just kind of showing that there's a bunch of different ones of 8.16. And Matthew's correlation coefficient of 0.53. And that's pretty good for a correlation. Finally, very quickly, we're going to do the same thing, but we're going to change it to multi-class. So in order to make it multi-class, we just cut it into 3 groups by quantile, all right? The lowest third is a 0, the middle third is a 1, the highest third is a 2. And that's it. We can see that they're about equal because we split it into thirds on purpose. And again, we're going to cycle through the number of neighbors from 5 all the way up to 150. Going to do 5-fold cross-validation, and this time we're just using accuracy. Accuracy is the percentage that were put in the right group. And just using exactly the same grid search as before, and fitting that, we'll get the predictions using cross-val predict after, and now a classification report. And we can see that it struggles a lot more in this case than it did with the binary one, especially in the middle. Which makes sense because the middle, it's like it's not very bad, it's not very good, it's just there. So that makes it hard to predict. And if we look at this confusion matrix, we can kind of see that as well. And what it really had a hard time with is predicting the ones in the middle. It predicted a lot of them were low. So there it is. That's the whole machine learning process in an example. So hopefully you saw that we started off with an understanding of the problem we were trying to solve. Now, because it was kind of a toy problem, there wasn't a whole lot to that. We knew that we wanted to predict house prices, and we knew that things that are important to house prices are probably like the number of bedrooms, the size of the house, whether it has a good view, things like that. Then you saw we got the data, and that was easy for us as well. We downloaded it from Kaggle using the Kaggle API. Then what we spent the most time on, and this is pretty normal, is exploring, cleaning, transforming, and engineering features. Now, we cleaned when we had to get rid of that one that had like 33 bedrooms, and we transformed a lot of our features because we wanted them to be more symmetric. mostly log transforms, but we did that Box-Muller transformation as well. And we engineered some features by taking some and making them binary. And again, that's probably the most common, like the longest one, the longest step. It takes a lot of work. There's a lot of creativity involved. It's very cool. It's a lot of fun. And then after we were done with that one, exploring, cleaning, transforming, and engineering features, then we encoded some features. Now in this case, we just left them. But like we talked about, if we had been using a different algorithm, we would have probably used a one-hot encoder, or because something like bedrooms is ordinal, 2 bedrooms is more than 1 bedroom, so it does make sense to have those be like in order. Then we could have used an ordinal encoder instead, and there's a lot of leeway and creativity involved there in choosing the encoders. Then we did feature selection, and what we used was a mutual information regression to tell us which features are kind of the most important. There are a lot of different ways you can handle that as well. Simply using a lasso penalty along with linear regression can do a lot of feature selection stuff for you. We'll talk about that in that linear regression course that we've got coming up. But in this case, we did mutual information regression and kept the 10 best features. Then we fit a model, all right, and we fit the model using cross-validation and a pipeline. We had to scale everything, and then we had to fit the KNN regressor or classifier, and then we evaluated the model. We looked at a whole bunch of different metrics. There's no point in limiting yourself to 1 or 2 big important metrics. Just use a bunch of them because they all matter. But what matters most is going to go back to step 1. How well do you really understand your problem? For example, if you really need to catch those true positives in a classification problem, then you're going to want to look a lot at the recall more than anything else. But in our case, we didn't have a real output of the model in mind. So there wasn't a whole lot to take into account when we were deciding what metrics to use. So we just looked at a whole bunch of them. We were able to get really good ROC, that ROC AUC score. So that was fantastic. I feel great about that. And then what you didn't see was the final step, 8, which was repeat. Now, the first time I actually ran that, I left a lot of those. I left a lot of the features not symmetric because KNN doesn't really care that much, and I got pretty good results from that. I think the AUC was like 0.78 or something. It was very high already, but then I went back through and like we just saw, I went through every single feature and cleaned it up and made it symmetric and made it kind of normally distributed and look good and everything. And then just by going back and doing that, I was able to raise, like I said, the AUC from about 0.78 up to 0.85, which is very good. All right, so hopefully that gives you guys an idea of the machine learning process. Again, step 1, understand your problem you're trying to solve. Step 2, get the data. Step 3 is to explore, clean, transform, and engineer features. I put those all together because you should be doing all at the same time. All right, step 4 was to encode your features. Step 5, I guess, was to select the features that you're going to use. And I mean, those last 2, those steps might include doing nothing. In this case, we didn't actually do any encoding. We did select features though, but a lot of the time you'll just use all your features. The next step is to fit the model, and then you have to evaluate the model. And both of those go back to how well do you understand the problem and how well do you understand your data. Different styles of data do better with different models, and different problems are solved by different metrics. And then once you've done that, you go back, change things, and do better. All right. So if you guys learned anything today, please give me a thumbs up. If you have anything to say, go ahead and leave that in a comment. And if you want to learn more, go ahead and subscribe to the channel. and I'll see you guys soon with that linear regression video.